Recording is rolling, so it is Tuesday, January 24th. We're going to finish up these ray diagrams from yesterday for reflection. Okay. Then, okay, I've got actually a practical real life example of that. It's pretty cool to show you guys. Then we're going to switch over and look at refraction. Now, refraction is like if light bends inside a medium, which is like this going on right here. Okay, so like it'll change angle. Okay. Ooh. So that'll be oh, and I've got a like a small lab activity for you guys. So I just gave you guys the supported page right here. So hold on to that for later, or you can write your name on it, right? So you guys got your name on this paper. Okay, save that for later. Tell you guys how refraction works. I've got some demos. There we go. So that's the agenda today. And so yesterday we were looking at ray diagrams for reflection. So we're still in reflection there, but we're thinking like mirrored surfaces, right? So think like mirrors, right? I'll get a recap of we got so far. So okay. We were saying like for a plane mirror, and this was not exactly a plane, but pretty close to a plane because the focal distance was really far away. Right? We're seeing the image should show up on the opposite side, like equidistant from the surface that the object is, if it's a true plane. Okay. We were looking at convex mirrors, right? Like looking at the backside of a spoon. And the convex mirror situation, like these top two are not really categorically different from each other, but yeah, you can like make an animation in your mind between the two frames. Like, okay, I can kind of see what happens when you go back and far away from the spoon. Okay. All right, then we were switched over. We started on concave. Now, concave is a bit more interesting because there's different categories of solutions that you can get depending on, say, where your eye is compared to the curved surface. So I have a few parabolic mirrors. Right, you guys saw this. You guys saw this, like this cosmetic mirror. Right, these are both, these are all parabolic mirrors right here that they're all concave. So the one that we left off on was an explanation for like the pink pig. Like, why does the pink pig look like it's hovering in front of the mirror? And the physics term for that is a real image, right? It looks like it's hovering in front. And it looks like what's going on is if your eye is outside the focal distance, right? So here's the focal distance, says something about how curved this is, and your eye is like out here, right? Let's go down to this very last one. What if your eye is inside the focal length, right? So here's your focal distance now. Right? Here's like your eyeball, right? Here's the mirrored surface. What does that look like? Okay. I'm thinking this is probably going to be the cosmetic mirror situation, and you guys know what that's for. It's like to blow up your face really big. Right? That's this right here. If you have this pretty close to your face, it's going to blow up your face pretty big. It has some concavity to it, right? So looking for that to be the answer, well, let's do the ray diagram and find out for sure. So remember, there's these rules where we use the same rules over and over on these diagrams. So one is we're going to have a laser light skirt at the top of this guy's head that's parallel to the ground. That's the first one we were making over and over, right? There's a million bajillion light rays bouncing all over the sky and the mirrored surface, but we just need a couple of rays to figure out where the image is going to be. And that's the first one, right? Parallel to the surface. That one's going to bounce off kind of down to the left-ish. Now, how much down to the left? Oh, well, it's going to go through the focal point, right? That's why we were identifying the focal point. It says something about how curved the mirror is. Boing. So you shine a laser light that way, it'll boing that direction. Or if you like, if you shine a laser light from this point through the focal point, it'll boing, bounce off parallel to the ground. Okay. I'm going to do some of that reflection that we just made though. I'm going to extrapolate up and to the right. So go ahead and extrapolate this way. Okay. Okay, guys got that? All right. Then the other light we were following was from the focal point to the top of his head, or top of his head to the focal point. Okay. And go ahead and take that all the way to the mirrored surface. Bam, just like that. All the way to the mirrored surface. Now it's going to bounce off, boing, back parallel to the ground. Like that. And then extrapolate that one to the right. Of course, you guys know no light actually crosses through the mirrored surface, but that's where it looks like the light ray's coming from. That be true? You guys got all that? Okay. And then, yeah. Thank you. where those rays cross here, right behind the mirror, that's where the image is going to appear to be. Now it's a virtual image because it looks like it's on the opposite side. Oh, and look, it's big. It's like blown up. Hey, that's like what a cosmetic mirror does, right? It blows up your image, makes your face look bigger. Like that. So if you hold it either like any kind of parabolic mirror, either pull that UFO apart with a pig inside it, or a cosmetic mirror, you hold it close to your face, looks like this. You hold it far away from your face, if you like invert your image, it looks like you're floating in front of it. Okay? But what about this middle one that I skipped? What if your eye is right on top of the focal point? Like, what's that going to do? Because these are like categorically different from each other. Right? So what if your eye is right on top of the focal point? Okay, you guys ready to do that? So let's just follow the rules that we did for the other 5. So light ray parallel to the ground, cross the top of his head. That's going to bounce off through this focal point, boing, just like that. Then there's a light ray, see, from the top of his head through the focal point. Okay. And that's where, well, that light ray, it's not going to touch the mirrored surface, right? It's kind of vertical, right? So this is where this whole thing blows up. So the answer to this one is that there's no image, right? In fact, if you do this, if you take a concave mirror and hold it like close to your face, then far away, okay, and put your eye right on top of the point, it just looks like a blur of light. Right? It just looks like a blur of light. Right? There's no real like image going on. You can discern. Right? So you guys go with those ray diagrams. Get ray diagrams. Right, so hang on to that for now. I'll have you guys turn this in by the end of class with that quarter page that I gave you guys that says Snell's law on it. Okay. All right. See you guys here. All right, let me flip the screen over here. And so I want you guys a pretty cool practical example of this. It's called whispering dishes. So they look like these satellite type dishes, and there's usually a pair of these, maybe across a field or maybe like inside a lobby. You might see these at science museums. I know that University of Florida, if you go inside the physics building, they have a pair of these in the lobby. And this is an acoustic mirror. So if you stand at the focal point of one of these dishes, right, just kind of like what we've been doing on the ray diagrams, right? And you whisper something that's like no one like beyond like 3 feet away could like ever hear you, right? That sound will actually be concentrated and reflect off the dish. It can be reflected across the field, across the lobby of the building. Okay? And if you have a friend standing at the other dish and they have their ear at the focal point of that other dish, they can hear everything you're saying, right? Like crystal clear. So if you guys ever get the opportunity to try that out, if you see a pair of those out somewhere, I've got a friend with you, try it out. You get it. There's also an inadvertent version of this called a whispering gallery. So usually these are set up accidentally. A lot of times any building that like has a dome in it or some kind of rotunda, like Capitol buildings, a lot of state legislators and even Congress too have these like domed buildings. So they're going to like be accidentally set up these whispering situations. So if you're staying at some particular focal point where the sounds like bounce off in a certain way, there can be like specific points elsewhere in the room where you can hear everything else someone's saying. So there are actual stories of like Congress people that like listen in on their fellow congressmen and hear like, stuff they're not supposed to hear. So whispering dishes. All right, so now we're going to move on to new stuff, refraction, because yesterday and first few minutes today we did reflection, right? So we're looking at reflection. All right, let's look at let's say stuff related to things like this here. Right? That's an example of refraction, right? So if you like shine in a light, it'll bend, right? Now it does turn out that each wavelength of light, like each color, will bend a little bit differently. Okay, so red doesn't bend very much, violet bends a lot, right? Or how about this? If you've ever like thrown a straw in a drink, right? Now it looks all bent out of shape. What's going on with that? Ooh, she got another one. It's pretty cool. An animation. Like reverse the direction of the arrow, right? All right, so this has something to do with light bending. Okay, so like how does light bend? Why would it bend? What does it have to do with these materials? It got glass here, got water, so I mean it's transparent. The light goes through it, but maybe not in a straight line. Okay, so check and see if there's any other demo I got lined up for you guys here. All right. Yeah, let's do a Paul Hewitt here. Paul Hewitt.
Inclined plane. And I got some wheels. And I'm just going to roll the wheels down the inclined plane. All right. What I'm going to do is I'm going to roll the wheels from a nice smooth sidewalk onto a rough piece of material. It's almost like wheels rolling along a sidewalk into the grass, or light coming down and interacting with the material and slowing down. If I roll them at an angle, did you see it bend? It came down like this and then bent. Let me put that on the board. My wheels are coming down in this direction, and they're coming from the smooth surface to the rough surface. When the wheels get to the rough surface, what happens to the speed of the wheels? Slow down. You know why they slow down? Because there's an interaction with the wheel and the material. Let's suppose it's like the little pieces of cloth on the towel, or maybe it's like blades of grass on a lawn, okay? There'd be some interaction, so this part would slow down. But what happens to this other part over here? It continues going quickly. So what happens, it sort of kilters. And so what happens is it goes like this. When both wheels get in there, they're going the same speed and they continue at a straight line. So there's no mystery as to why the wheels will kind of bend over, is there? I mean, if you can move along like that and something's on the way, won't your arm go like this? I mean, part of it slow. Well, guess what behaves the same way? Light waves. When waves of light come from above, say hit water. Maybe the waves of light that come from the sun, like that. We got a ray coming down like that. Incidentally, it turns out a light ray and the wave fronts that represents, these are like the crests of waves. Think of water waves, yeah? Right angle in here again. Always a right angle. See, even the axis of a wheel and the direction of which it's traveling, right angle. See? So what happens over here? These waves of light come down, and when they hit the water, what happens to the speed of the waves? Oh, you don't know that. Well, check your neighbor. Oh, they somehow go faster. What's the answer, gang? They slow down. Okay, the waves slow down. So what happens? They bend, and they sort of bend like this, and they get closer together. So the wavelength gets a little less in here, but the frequency of the wave stays the same.
All right, so switch back over here. I'm gonna draw some similar to what he did, and I'm gonna add to that. I'll continue this here. All right, so I got this boundary between two different media. And so maybe I'll have water here and air here, maybe something like that. Okay. You draw some fish down here, so you guys know. Got some water going on down here. And you guys remember here, if that's the boundary we're interested in, I'm going to draw a normal line to that boundary. Maybe I'll break out a protractor, make sure it's exactly 90 degrees to that. So 90 degrees, bam, right there. Okay. Guys, remember yesterday we were drawing some normal lines, say to a mirrored surface, and then measuring angles with respect to that. This is leading to an equation called Snell's law, and there's going to be some angles involved, and the angles are going to be measured with respect to that normal line. Right? So here comes an incident ray. So we got like a ray of light. Right? I'm going to aim it straight for like that normal line right there. It's kind of like the thing called here, bam, like that. So there's a ray of light, and the ray of light is going to bend in the water. Now, and the water gets this angle to the normal line is going to get smaller. Okay. So see, like that angle there is kind of big, and this angle here is kind of small. It's that. Okay. So angle inside of the air, I'm gonna call it the incident angle, and the angle inside of the water, I'll call it the refracted angle. So bending in physics is called refraction. So incident angle and refracted. This is all for refraction. Okay. Now that ray of light, I'll do the same thing that Paul Hewitt had. I'm going to draw all the wavefronts because you guys know light is a wave, like it's a transverse wave. So maybe you got a bunch of wavefronts that's like, they look kind of like this, for example. Something like that, right? Right. So got transverse wave, like pressed, 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 pressed. All right, and just keep going. Right. But when it hits the water, now light will slow down. Now, the thing about slowing down, you guys know a wave equation that goes like this. Speed is equal to wavelength times frequency. You guys remember that? So V is speed, lambda is wavelength, and F is frequency. Some textbooks use like a Greek character called nu for frequency. It looks kind of like a V, but it's kind of confusing. So just use M. Okay, got that. And so you guys remember this. Right? And then now if we're talking about light, right? This is light, right? Shouldn't I be using speed as 3 times 10 to the 8 meters per second? Maybe we should call that a C, right? Which would be okay. It's strictly true in a vacuum, right? Light only travels 3 times 10 to the 8 meters per second in a vacuum, right? Through the air, it's a tiny, tiny, tiny bit slower, but it's almost a vacuum, so we'll basically treat it that way. But through water, it's significantly slower, right? And I'll show you guys how much slower here in a few minutes. Again, after the notes, but just for now, it's big picture concept here, right? You guys see these wave crests? Right, so I got, oops, let me continue this one a little bit right here. Right, bam, 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 bam. Right. See all those wave crests leaving the air? Hey, wouldn't the wave crest entering the water also have to line up with those exact same wave crests? Right? So when I draw the wave fronts in the water, another way to say that is that the frequency of the wave crest leaving the air equals the frequency of the wave crest entering the water. So leaving the air, entering the water has to be the same. And so this. So these all have to line up. Okay. So frequency is going to be the same, but the speed changes. The speed decreases going from the air to the water. It slows down. Guys, if this decreases and this stays the same, then doesn't wavelength have to also decrease? Right, decrease. Right? And you can see that right here. See how these wave fronts get like closer to each other? You continue this, about something like this. So like now it's like pressed, 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 pressed. See like a long wavelength here. I'll call this like lambda in the air, and then a short wavelength here. I'll call this lambda water. Right? Okay, that's it. Okay. Now, how much will the light ray bend? Well, it depends how much it slows down. So you guys see slowing down is going to cause bending. That's what this whole explanation was about. Okay. Well, it'd probably be different for water than it would be for like different kinds of glass or for maybe something else, right? Or maybe like whatever this is, right? Ooh, you guys can see some refraction going on right there too, right? See that? What is that? So there's something called the index of refraction that you can quantify, like how much light will slow down. So for air, I'm going to call it like 1.00, which it's actually like 1.00003, something like that. And for water, it's like 1.33, right? And what index of refraction is the ratio of what is the speed of light in a vacuum to the speed of light inside that particular material. I'm going to write that down. Yeah, write some new notes right here. Okay. So talking about index of refraction. Okay. I'll call that N for index of refraction. Okay. And that's equal to the speed of light in a vacuum, which is C, 3 times 10 to the 8 meters per second, compared to the speed of light inside that material, which is going to be slower. Right? Light slows down inside these materials. So here's the speed of light in a vacuum. right, which has a number to it. I mean, this is one of the fundamental constants in nature, right? 3 times 10 to the 8 meters per second. Okay. And here, v is the speed of light inside the material. Um, like water, glass, something like that. Or you could say medium. Never said it, medium. Right. Right. So what are these, what are some values for index of refraction? Like if you take this ratio for different materials, it's like material property, right? So for a pure vacuum, it would, well, in a vacuum, it would just be C over C, which would be exactly 1, wouldn't it? To be like 1.000, like exactly 1 for a vacuum. Okay. Now for air, it actually isn't a whole lot different. It's like 1.0003. So like in the lab activity today, I'm just going to treat the index of refraction there as basically 1, just like kind of like it's a vacuum. This could be. Can't really distinguish between these two. Now for water, okay, now here's where there will be a significant difference. I mean, if you guys look inside a pool of water, you can see like everything's clearly refracted. Okay? So it's 1.333. I might just round that to 1.33, something like that. But okay, so it's like basically like slows down by 33%. You can think of it that way inside water. I've got one more of my notes ready to go, which is diamond. I thought this one was interesting because it's a pretty big one. It's 2.42, right? Maybe we should have glass on this list. I don't, maybe because there's like different kinds of glass. So I don't have it for glass, but you know what? The lab activity today, we're going to figure out what's the index of refraction for this. This feels like glass. So it's kind of tricky plastic, but it might be glass piece. I'll call it glass. All right, you guys got that? All right, and then I need one more equation to tie this all together, because how are these indices of refraction related to these angles, right? This angle of incidence relative to this normal line, this angle of refraction relative to this normal line. Okay? And the equation that ties it all together is called Snell's law. So here's Snell's law. It says the following. Index of refraction times sine of the angle is equal to the other index of refraction times sine of the other angle. So index of refraction of air times sine of the incident angle is equal to index of refraction of water times the sine of the angle of water. So then we're back to the same game we've been playing since August, right? If you know any 3 of these variables, you can solve for the 4th one, right? So if you know the 2 materials to work with, their indices of refraction, and you know the angle that you're shining the light in, you can calculate the angle that's going to refract at. Maybe you have to apply like an inverse sine. Okay? Or how about this? Maybe you don't know what the material is, but you know, like, okay, so air is pretty close to vacuum, and then you shine the laser light through and get a couple of angles, then you can calculate what that N2 is. And that's actually closer to the activity that we're going to do today. Okay. Right, so you guys good? So one more thing before we head over to this activity. I want to show you guys the video demo version of this. Okay, so I switch my screen over here. Okay, I'm gonna play a couple of demos. Here we go. Snell's law. Oh, look at that. It's a semicircle glass piece, just like I was showing you guys. Okay. Right, so this flat light here, this is the boundary between the air and the glass. And look, he already has a normal line set up. And if you can read, okay, well, he just covered it, but it says, oh, there it is, normal. You guys see it says normal? Oh, that's because it's perpendicular to this interchange right there. Okay, so let's see if he shines the light like pretty well head on, like perpendicular to the surface. There's like not really any refraction going on. But the more he changes that angle from the normal line, the more and more pronounced the refraction is. So scroll ahead a little bit. You guys can see it now. So it looks like he's shining in at, what is that, 10, 20? Yeah, 30 degrees. And it's shining out at like 20. Yeah, so there you go, like 30 and 20. So just from that, you could figure out what is the index of refraction of that glass piece, right? So it's going to go on more and more. Let me speed ahead a little bit. You guys get the idea here, right? Ooh, do you guys see some reflection showing up here? Right? See, like if I zoom back, if I rewind, I don't know, I can't see any reflection, or maybe it's like really faint. But here again, so the reflection is getting stronger and stronger, and the refraction is getting like weaker and weaker. Now, something else, if you're thinking ahead, if you're animating this in your mind, you might think, hang on, what's going to happen when this angle of incidence right here, gets close to 90 degrees? Okay? Because the refracted angle is not catching up as fast. You guys see that? Ooh, so do you think it's going to like run out of steam at some point? Huh. Right, let's see how far we can go with this video. Right. Ooh, so there's some really strong reflection and really weak refraction. Okay. So he's up to what, like 80 degrees incidence angle. There's 85 degrees. And I think it's about as far as we can go. So do you guys see that the refracted angle is like a little over 40 degrees, I think, like 40 up here, like 42 degrees about, something like that. So that angle has a name. It's called the angle of, it's called the critical angle, right? So like this critical angle could be like 42 degrees about, maybe I'll call it like 42 degrees, okay? Which, if you think about it, doesn't that mean that like, suppose you wanted to refract the light through and you want it to refract out at 60 degrees. Okay? Could that ever happen? No, you're just out of luck, right? So maybe that could be useful for like, say you're like trying to like hide behind something or like around a corner, or like, oh man, how do I hide behind this glass piece? It's transparent. Well, if I hide behind like this critical angle, if I'm not out here like 60 degrees, right, no light will ever like transfer to that point. So you're like permanently hidden. I think on my poster version up here, do I have like a guy in a boat or something? Do you guys see like a guy in a boat, one of these posters? Right? And there's like a fish. Do you guys see like a little goldfish down there? Will that guy in the boat ever see that goldfish? No, because he's like outside that that critical angle, right? You guys see what I'm point out? Is that? One more detail, a little detail I meant to mention, right? Do you guys see how there's only one place that actually refracts, and that's at the flat part, right? But the fact that this is a semicircle, right? Once it bends, once it refracts at that point, why does it not bend? Why does it not refract again when it leaves the curvy part? Exactly. Yeah, because as long as the light is emerging from the center of the circle, it's always going to emerge perpendicular to the surface, right? So then it won't bend again. Right. The other one I want to play for you guys is, let's turn this whole thing around. Do the same thing, just from the opposite side, right? Because this is a faster way to find the critical angle. So you guys saw it was like about 42 degrees it looked like. So you guys see it's just the same thing upside down, right? But now I bet you can't go beyond about 42 degrees, because now the refracted angle going into the air is growing faster than his incident angle in the glass. Right? There's 40 degrees, and then just a little over 40. About you guys see at 42, it went to 90 degrees up here, and then right. Oh, and then after that, you get total internal reflection. You guys see total internal reflection? That's actually the title of this video, or at least what I called it. Is that? All right. Okay, so if you shine it at like 50 degrees, there would be no refraction at all. Right, so we're gonna try this in class. Right, so this one, I'm just gonna guide you guys through. It's just the design we got for this particular lab today. Right, so got this class piece. You guys got the quarter page, right? So I'm gonna follow along with the guys with the quarter page. Okay. Did you guys write your name at the top? You wrote your name at the top of the quarter page. So by the end of class today, I'll have you guys turn the quarter page and also your reflection ray diagrams from yesterday. And if you hadn't finished either one of those for any reason, then you guys know I post all these videos to Google Classroom, so you can go and just find the video and then fill in the details there. All right, so let me trace this thing. All right, so I'm gonna put that back in place, but I need to see the center. I can find about the center of this thing. Bam, right about there. Let me go to 90 degrees. Bam, right there. Need to get a normal line. There's my normal line. Extrapolate that a little bit. So normal line is right there, right? So all the angles that I'm gonna measure are gonna be with respect to that normal line, right? Break that up. Okay. Let's put this glass piece back in place. Okay. On this paper, okay, you write your name on the paper. So I got a couple of columns for the angle, and then a couple columns for to do calculation, something about the sine of the angle. Oh, okay, so it's going to feed into Snell's law, right? And there's two things that I want to find on this. Let me zoom in here. You guys can see. I realized after I printed these and cut these up, there's two slightly different versions of these, but that's right. You get the same thing here. Yours might say what mine says in glass. In glass is the index to refraction of the glass. Okay? The other thing I want to find is what is the critical angle? What is theta sub c? So if you have a paper that looks like mine, then underneath the box, write theta sub c. That's the critical angle. Okay. And if you have the other paper, then it probably already says theta c in it. Okay. And if you have that one, just write into glass beneath that. So we got in glass and theta c. All right. And then at that point, everybody's papers are essentially identical. Okay. Okay, so we're going to find both. Actually, if you know either one of those, you can calculate what the other one is. Right, so we're going to do a little bit different perspectives. Right? Hopefully, they'll be pretty close to each other. Okay. So figure this out. And so put this guy back in place. Bam, right there. Okay. Take out my laser, and I start marking paths. Paths for this laser shine through. Okay. So I do exactly what I did on the demo. Oh, zoom out a little bit. Okay. So you guys see this laser light aiming straight for the center of the circle. Notice I'm not like aiming over here. I mean, I could, but it'd just be kind of messy. So right there, you can see, see how it refracts out here? So I'm going to trace this laser light. So it's going in that direction. And it's emerging, refracting. Bam, like right there about. So trace this path. So there's the path of that light. Okay. So I'll call this the incident angle, theta sub I. I'll call this the refracted angle, theta sub R. Okay. And let's get a measure for each of those. Okay. Now you guys have used a protractor lots of times in this class. Okay. So you guys know I'm going to take the node of the protractor, park it right up there. I'm going to zero out the normal line. And the angle of incidence looks like 51 degrees. And the angle of refraction looks like 33 degrees. So over here, you go 51 degrees and 33 degrees. Okay, just like that. Okay. Okay. So let's take the sine of those angles. Sine of 51 degrees is 0.777. Sine of 33 degrees is 0.545. Okay. You like Snell's law and figure out what is the index of refraction. Right, so let's do a few more of these though. So put this guy back in place. A couple of different paths. What if I do kind of a shallow angle? Let's see what this is. So here's my incident angle, you're close to, and here's my refracted angle about. So I got this. This is this. So plus theta I here. Okay. Oh, I changed the color, but it's gonna be different. And theta R. Right, so we got like a peak path. This is right, so angle of incidence I've got as call it 25 degrees, I think. 25 degrees. And the refracted angle looks like I think 15 looks 15. What is sine of 25 degrees is 0.423. What is sine of 15 degrees? 0.259. I want to get one more. So how about this dark blue ink right here? Try that. Try a big old angle right here. Oh, you guys see some really good reflection and kind of a weak refraction, but there's enough refraction to make this work. And you know, so about there it looks like somewhere. Okay, that's as best I can get it. So the angle of incidence is so, yeah, I call it, yeah, about 70 degrees right there. So theta I is 70 degrees. And the refracted angle looks like 39, I think I'll call it. 39 degrees. Sine of 70 is 0.940, it rounds to. And sine of 39 degrees is 0.629. There we go. Now, if you go back to Snell's law that we flashed it here a few minutes ago, okay, let's take that and rearrange it a bit because it's kind of like we're solving for N2 in this case, right? We're solving for N2. We'll write that here. So N1 sine theta 1 equals N2 sine theta 2. So if I'm solving for index of refraction of the glass, wouldn't N2 equal to N1? Oops, N1 times sine theta 1 over sine theta 2. Okay, that'll be right. And index of refraction of air is, I mean, it's so close to vacuum that we wouldn't be able to tell the difference in this classroom. So I'll just call that 1. I'm just going to call this guy 1.0. Okay. So really, it's just the ratio of the sine values, right? Sine theta infinite over sine theta refraction. Okay. And so really, we just have to take this ratio here. Okay. Let's get each one of these. What is 0.777 over 0.545? That is 1.43 it rounds to for the first one. Let me jot that down. So in glass is 1.43 from that first calculation. For the second calculation, what is 423 over 259? It's 1.63, it's saying. 1.63. How about the third one? What is 940 on 629? 1.49. Okay, something like that. Okay. Let's get an average of those. Right, so look at maybe like n bar, like an average value. What's the average of those three? What is 1.43 plus 1.63 plus 1.49, all divided by 3. It says 1.51, so that'll be the answer to this. The index to refraction of glass is 1.5167. Maybe we'll call it 1.52. How about that? 1.52. Okay. Now, since this is, I think this is like high school science equipment here. It says like glass block on it. Imagine they probably manufactured it for like some specific value. So I'm going to guess that the actual value is like 1.5. I don't know for sure, but that's probably what it is. It's probably 1.5. Okay. Now, I still want to get the critical angle for this though. Still get the critical angle. Okay. So let's get that experimentally. The way I'll get it experimentally is one more laser light here. Okay. We actually shine it through the other direction and change the direction until the refracted angle like goes to 90 degrees from the side. Okay. Now, here's okay, so here's emergent here. And change the angle. Ooh, now it's getting really close to 90 degrees. And okay, probably right about there, so it goes to total internal reflection. Like that is, but that's probably as close as I can get it. So let's see. What is this angle and what did it agree with the critical angle that we got with the index of refraction we got earlier? Okay. So I'm calling this angle right here theta sub c, right? Like the critical angle. Let's see what that angle is. So zero out the protractor with the normal line. It does look like 42 degrees, I think. It's like 42 degrees. So for critical angle, put 42 degrees. Right, 42 degrees. Okay. And there's the last thing I want to do with this lab is which is this. This critical angle and this index of refraction, they should like agree with each other. Like if you know one, you can calculate the other. Right, and I can show you guys how you do that. Well, just take this lab page and do the calculation on the other side here. Okay. We're going to see how close. Okay. So Snell's law, n1 sine theta 1 equals n2 sine theta 2. Okay. Let's say let's do this. We haven't done this yet. Let's solve for what the critical angle should have been, given that we know what the index of refraction is. I hope it's pretty close to 42 degrees, but we need like an inverse sine because we haven't done that yet, right? So index of refraction of air times sine of 90 degrees. Guys, what is sine of 90 degrees? Yeah, that is 1. So okay, so all this is just equal to 1. Equals n of the glass times sine of the critical angle. Okay, so this critical angle would correspond with this other angle being 90 degrees. Okay. So it looks like sine of the critical angle in general is, since you know the sine of 90 degrees is 1, just 1 over the next refraction of the glass in this case. Okay. You guys remember how to extract the angle from a sine function? You have to apply an inverse sine, right? Sometimes called arc sine. You guys remember that, right? 1 over n glass. Okay. Well, there it is in terms of variables, so that could like solve anything. Okay, but let's do it for this specific problem. Because we were getting like what 1.52, like that. Let's see what this comes out to. What is inverse sine of 1 over 1.52? It is, oh, look at that, 41.1 degrees. That's so close to what we measured, right? Okay, so I'm really happy with that. Ooh, I think this is a good video to take right here. All right, you guys get it? So the calculation agrees with the empirical measure. Okay. All right, questions so far? Okay, so here's what we do. I'm gonna flip my screen over and play you guys some more demos about refraction. So by the end of the class today, just turn in both that quarter page and also your ray diagrams that we were doing yesterday and today. Okay, and then I'll do that.
Mr. Griffin,
Yeah.
I wasn't here for part of the class for the diagrams,
Oh, okay. So just get the videos on Google Classroom.
and then I can turn it into.
Yeah.
Okay.
Bird.
Thank you.
You know,
All right.
if you're like driving and you have a road surface and the light is coming down hitting, it turns out the light that will make up the glare is polarized in the same plane as the surface. Do you ever take these scaly rocks and go out in a pond and you get flat rocks and you want to scale them across the surface? If you take the rock and you throw it kind of flat, sort of like this, okay? Boom, it'll boom, bounce off, yeah? How about you throw it like this? Kind of go down, yeah? Light does the same thing. Light that's coming down like this, bounce, huh? Light that's coming like this, it's absorbed. So that's why you get the glasses. What kind of Polaroid glasses would you wear to cut out glare from horizontal surfaces? Let me show you 3 pair. Which would you use, gang? These are these for driving. You got a truck driver and you're gonna drive along the road. Which pair of Polaroids? How many say they're all the same?
Alright, here, I have to beat the bell on this one. So guys, if there's a bunch of horizontal light coming in, you see a horizon, blah, blah, blah. Don't you want to cut out all that light? So you guys want to use the second pair, right? Use the second pair because that will allow all the vertical stuff come through. So it'll provide more clarity. Okay? If you ever have polarized glasses, one thing you do is take a couple pairs of polarized glasses, put them in front of each other. They'll like, if you put them 90 degrees to each other, they'll cut the light out, right? How about this? This last pair, what's that useful for? Why would you want one image in one eye and one image in the other eye? If you're watching a movie that's 3D, that 3D movie right there. All right. So I got all your guys' papers in the great tray. All right, that is a wrap on today.